Okay, this is chapter 8.5, the end of chapter 8, and it's using recursive rules with sequences. The essential question is, how can you define a sequence recursively? A recursive rule gives the beginning terms of a sequence and a recursive equation that tells how a sub n is related to one or more preceding terms. So what you will learn in this video is how to evaluate recursive rules for sequences, write recursive rules for sequences, translate between recursive and explicit rules for sequences, and use recursive rules to solve real-life problems. Okay, so let's take a look. Okay, so before I get to example 1, this was in the text, evaluating recursive rules. So far in this chapter, you have worked with explicit rules for the nth term of a sequence such as a sub n equals 3n minus 2 and a sub n equals 7 times 0.5 to the power of n. An explicit rule gives a sub n as a function of the term's position number n in the sequence. In this section, you'll learn another way to define a sequence, and that's by a recursive rule. A recursive rule, not an explicit, but a recursive rule gives the beginning terms of a sequence and a recursive equation that tells how a sub n is related to one or more preceding terms. So if I get rid of this and we get to example 1, we're going to evaluate a recursive rules here. So write the first 6 terms of each sequence where a sub 0 is 1, and the rule a sub n equals a sub n minus 1. Well, that just means the term before the nth term, and then you add 4 to it. So for starters, all we do is say, well, a sub 0 equals 1. Okay, that was easy. And then what is a sub 1? Well, a sub 1, that'd be here. So I'm just focusing on this right now. Actually, I don't want to do that because I'm covering some of it. Let me move it over a little bit more. So let me just do this. A sub 1 would be a sub 1 equals a sub 1 minus 1 plus 4. Well, a sub 1, therefore, well, 1 minus 1 is a sub 0 plus 4. So all we're doing is taking a sub 0 plus 4. So let me get rid of this here. I just wanted to show that. Okay, so a sub 1 equals a sub 0 plus 4, which equals, well, a sub 0 is 1 plus 4, so a sub 1 equals 5. Okay, so that's what we're doing here. So continuing, it says write the first 6. So there is the first 2. A sub 0 is the first term, a sub 1 is the next, a sub 2 would be the third term, and that's going to be a sub 1 plus 4. And a sub 1 was 5 plus 4, therefore that equals 9. Okay, so we're going to keep doing this. A sub 3 equals a sub 2, because it's a sub 3 minus 1, a sub 2 plus 4, and a sub 2 was 9, and 9 plus 4 is 13. A sub 4 equals a sub 3 plus 4, and a sub 3 was 13, so a sub 13 plus 4 is 17. And finally, a sub 5 is the term before, plus 4, which is 17 plus 4, which is 21. So the first 6 terms are 1, 5, 9, 13, 17, 21. So it's 1, 5, 9, 13, 17, 21, and so on. So there are the first 6 terms of this sequence. Okay, so here we go. Here's the next one. So f of 1 equals 1. So f of 1, the first term, equals 1. F of 2 is going to equal 3 times f of n minus 1. Well, n is 2 in this case, so that'd be f of 2 minus 1, which is f of 1. So 3 times f of 1 equals 3 times 1, which equals 3. F of 3 equals 3 times f of 2, which equals 3 times f of 2 is 3, which is 9. F of 4 is going to equal 3 times f of 3, which is 3 times, and f of 3 was 9, so that's going to become 27. f of 5 is going to be 3 times f of 4. And f of 4 was 27, so it's 3 times 27, which is 81. And finally, f of 6, our sixth term, is going to be 3 times our fifth term, 3 times f of 5, there's a dot there, equals 7 times 3 is 21, 3 times 2 is 6, whoops, I'm sorry, 3 times 81, which equals 243. So our first 6 terms would be 3, no, our first term is 1, 1, 3, 9, 27, 81, 243, and those are our first six terms, and it continues. Okay, so that's how you evaluate recursive rules. So now you should be able to do problem numbers 3 and 6 in your exercises. Okay, core concept, recursive equations for arithmetic and geometric sequences. Arithmetic sequences are a sub n equals a sub n minus 1 plus some common difference d. Okay, and the geometric sequence is a sub n equals our common ratio times a to the n minus 1. So there are the equations for arithmetic and geometric recursive equations, and we'll use those in the next examples. Okay, example 3 is writing recursive rules more. So it says write a recursive rule for each sequence. So if I look at this, I say, okay, well, 1 plus 1 is not 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. So 1 plus 1 is 2. So 1 plus 0 is 1. So what I'm saying is there is no common difference. 1 plus 1 is 2, but 2 plus 1 is 3, and 3 plus 2 is 5. So there's no common difference. And then when I take one term before the other, 1 over 1 equals 1. But then the next one, 2 over 1 equals 2. So there is no common ratio either. So when there's no common difference or no common ratio, what you do is say, well, a sub 0, or not a sub 0, a sub 1 equals the first term, which is 1. A sub 2 equals 1 as well. All right, so a sub 1 equals 1 and a sub 2 equals 1. So I have to try to come up with a rule. So a sub n equals, so we have to try to figure out what's going on here. This is a famous ratio, by the way, a famous sequence, and I'll get to that in a minute. But if I put a sub n equals a sub n minus 2, so a sub 1 would be a sub n minus 2. This is a sub n minus 2 plus a sub n minus 1. So what am I talking about here? Well, 1, 2, 3, 4, 5. So let's take a look at 5. So if I have a sub 5, well, that's going to be a sub 5 minus 2 plus a sub 5 minus 1. And what is a sub 5? 1, 2, 3, 4, 5. It is 5. So 5 minus 2 plus 5 minus 1. Well, 5 minus 2 is 3, and 5 minus 1 is 2. And that comes out to be 5, which is what our term is. So let's try that again. A sub n equals a sub n minus 2 plus a sub n minus 1. There's our rule. And now let's look at the fourth term. So a sub 4 is going to equal a sub 4 minus 2 plus a sub 4 minus 1. So a sub 4 is 3. So that's going to be 3 minus 2 plus 3 minus 1, which equals 1 plus 2, which is 3. And the fourth term is 3. So there's our rule. So what you do is you take the nth term, subtract 2, and then add that same nth term and subtract 1. Okay, so it's a really strange formula, but once we get it, once we figure it out, then we have a rule. So the rule for that is, I shouldn't have erased it, a sub n equals a sub n minus 1 plus a sub n minus 2, or minus 2 and then minus 1. It doesn't matter because addition is commutative. Okay, well, this is called the Fibonacci sequence. Fibonacci was an Italian mathematician, and he came up with this. And it's basically growth reproduction, like rabbits. You have 1 and 1, now you have 2, then you have 3, then you have 5, then you have 3 plus. So what's happening here is, what's 1 plus 1? Well, it's 2. What's 1 plus 2? It's 3. What's 2 plus 3? It's 5. What's 3 plus 5? 8. What's 5 plus 8? 13. 13 plus 8. 13 plus 21. And it just goes on and on and on and on and on. Forever and ever. Okay. So that is the Fibonacci sequence. So the rule for the Fibonacci sequence is the term you're talking about, minus 2, plus the term you're talking about, minus 1. Okay, this one, 1 plus 1 is 2. So the common difference here is 0. Common difference here is 1. So it's not common. So there is no common difference. So I shouldn't say the common difference. I should say the difference is 0. The difference is 1. They're not common, no common difference. 1 divided by 1 is 1, but 2 divided by 1 is 2. There is no common ratio. So since this does not have a common difference or a common ratio, we can denote the first term by a sub 0 equals 1. A sub 1 equals 1. A sub 2 equals 2, and a sub 3 equals 6, and a sub 4 is 24. So I'm just going to do that first. And then, so what can we do with that? So a sub 1 equals 1. And that's equal to 1 times a sub 0. So I'm just looking at a sub 1 now. So what does a sub 1 equal? Well, it equals 1 times a sub 0. Because a sub 0 is 1, and 1 times 1 is 1. So that works. So let's try that. So a sub 2 equals 2 times a sub 0. Which is a sub, I'm sorry, 2 times a sub 1. It is also a sub 0, but we don't want to use the same one every time. So this is 2 times a sub 1. 2 times a sub 1, well, a sub 1 is 1. 2 times 1 is 2. And sometimes you might have to try a few things here. Just be tedious and have some grit here and try to figure it out. So now if I take 3 times a sub 2, what happens? Well, a sub 2 is 2. So that's going to be 3 times a sub 2, which is 2. And I did, in fact, get 6. And I'm going to try it one more time. A sub 4 is going to equal the number of the term. A sub 4 is 4. Actually, no, a sub 4 is not 4, it's 6. So a sub 3, a sub 4 is going to be 4 times a sub 3, which is 4 times 6, which is 24. So all you're doing is taking the number of the term, which is n. So it's n times the term before. So now I have a sub n is going to equal n, the number of the term, times a sub n minus 1. So I'm just taking the number of the term times a sub the term 1 less. 4 times a sub 3, 3 times a sub 2, 2 times a sub 1. And if I kept going, this would still work. So a sub 5 would equal 5 times a sub 4, which is 5 times 24, which is 5 times 4 is 20, 5 times 2 is 10, that is 120. So there is the recursive rule for this sequence. Okay, so now you should be able to do problem numbers 14 and 20 in your exercises. Okay, example 2 now is going to be writing recursive rules. So it says write a recursive rule for a 3, 13, 23, 33, 43. So you can simply see that we're adding 10 every time. 3, 13, 23, 33, 43, 53. So our first term is 1. Our n is 1 for our first term, and our first term, a sub n, is 3. So n equals 2, that means a sub n, or our second term, well, that's 13. And our third term, n equals 3, our third term is 23. And when n is 4, that's our fourth term, that is 33. And then our fifth term is 43. So that's how you do this. So the first thing you want to do is use a table to organize the terms to find the pattern. And then you're going to say, okay, well, I had to add 10 here. I had to add 10 to get 13 to 23. 23 plus 10 is 33. 33 plus 10 is 43. So my common difference, D, equals 10. So I write the formula, a sub n equals a to the n minus 1 plus D. And that's all there is to it. So that's A. So our recursive rule is a sub n is the term before plus 10. Okay, and then now we're going on to the next one. So our n being 1, meaning first term, is 16. Okay. When n is 2, that's our second term. Our second term is 40. When n is 3, that's our third term. And our n is a sub 3 is 100. And our fourth n, our n being 4, fourth term, is a sub 4. That's our fourth term. That's 250. And then 5, our fifth term, is 625. So when I look at this, I take 16, I have to add 24 to get to 40. 40 plus 24 is only 64. So it's not addition. So we have to find a common ratio. So off to the side, I'm going to say 40 divided by 16. Well, 4 will go into 40 10 times, and 4 will go into 16 4 times, and that will reduce again to 5 halves. Okay. So if I pick any other one, they should all be the same. 100 divided by 40 is the same as 10 divided by 4. Well, that reduces to 5 halves. The computer just went wacky on me. 5 halves. Okay, so this is times 5 over 2. This is times 5 over 2. And you can check it. And this is times 5 over 2. And this is times 5 over 2. Okay, so rather than just a dot there, I guess, because that looks like 0.5 over 2. Let's just put an X. So it's times 5 halves, times 5 halves, times 5 halves, times 5 halves. So that is our common ratio, is 5 halves. So our rule for when it's multiplication, or geometric, see, this is arithmetic, you're adding, geometric, you're multiplying. So a sub n equals r times a sub n minus 1. Okay. I didn't finish this over here, by the way. I will go back. So a sub n is going to equal my common ratio, 5 over 2 times a to the n minus 1. Okay, now I didn't write this out over here. I said it and I never wrote it. So a sub n is going to equal a sub n minus 1 plus our common difference, which is 10. So this is the answer to A. And this is the rule for B. Okay, so that's how you write recursive rules. Now you should probably be able to do problem numbers 12 and 13 in your exercises. Okay, example 4, translating from explicit rules to recursive rules. So it says to write a recursive rule for a sub n equals -6 plus 8n, and then this one. So let's look at A first. So here's A. So we have a sub n equals -6 plus 8n. I want to find out what the first term is. So a sub 1 is going to be -6 plus 8 times n, which is 1. So our first term is going to be -6 plus 8. So a sub 1 is going to equal 2. Okay, so we found our first term. All right, and so if I do a sub 2, I'll do a different color. A sub 2 is going to equal -6 plus 8 times 2. So all we're really doing is adding 8 each time. 8 times 2 is 16, 8 times 3 is 24. It's a common difference of 8, but I'll just keep going. So a sub 2 is going to equal -6 plus 16. So a sub 2 is going to equal 10. So to get from 2 to 10, you had to add 8. So if I do one more, a sub 3 equals -6 plus 8 times 3. A sub 3 is going to be -6 plus 24. A sub 3 is 24 minus 6 is 18. 2 plus 8 is 10. 10 plus 8 is 18. So we found the rule. So a sub n equals, actually you want to say what your first term is first. A sub 1 equals 2, comma, a sub n equals a to the n minus 1 plus 8. Okay, so there is the rule for A. Now let's take a look at B. Okay, so A is a arithmetic sequence because we have addition. When you see this, an A times a B, if you will, it's an exponential function, it looks like, that is a geometric sequence. So we have a geometric sequence, and let's find A sub 1. So this is B. So A sub 1 is going to equal -3 times 1/2, 1 minus 1. So A sub 1 is going to be -3 times 1/2 to the 0. So A sub 1 is going to be 1/2 to the 0 is 1 times -3 is -3. So our first term is -3. Okay, so we found A sub 1. We want to write a recursive rule. Well, we're multiplying by 1/2 every time. So our R equals 1/2. So I want to write A sub n equals R times A sub n minus 1. And A sub n is therefore going to equal 1/2 times A sub n minus 1. And A sub 1 equaled -3. Okay, so all you really need to do for these when it says to translate explicit rules to recursive is determine what the first term is and then write the rule. Determine what the first term is and write the rule. So geometric is addition, or I'm sorry, arithmetic is addition, and geometric is multiplication. Now you should be able to do problem numbers 29 and 34 in the exercises. Okay, here's example 5, translating from a recursive rule to an explicit rule when they give you a first term and the rule. Okay, so the recursive rule. So what I'm going to do is say, okay, well, A sub 1 in this case is -5. And this -2 right here is our common difference, D, and that's -2. So I know my first term, A sub 1, and I know D. So then I write my rule. So A sub n equals, and it's the first term, A sub 1 plus the number of terms -1 times the common difference. Okay, so there's our rule. And we write A sub n equals, and then we just substitute in. Well, it's -5 plus, and then it's n minus 1 times -2. Okay, and then I'm going to distribute that. So A sub n is going to equal -5 plus -2n plus 2. When I distribute here, I get -2n plus 2. So now that's going to simplify because I have a -2n and a -5 plus 2 is -3 plus, well, it's not plus a negative. We don't ever want double signs when we're done. So my plus a negative is -2n. So our recursive or our explicit rule from the recursive rule in the first term is A sub n equals -3 minus 2n. Okay, so there's the explicit rule. Here we have a sub 1 given 10, and this is multiplication, so this is a common ratio of a geometric sequence. And our common ratio R is the term in front, which is 2. So I know a sub 1 is 10 and R is 2. And the recursive rule is a sub n equals R times a sub n minus 1. Okay, so you write the rule and now we substitute our givens in. So a sub n is going to equal R times a sub n minus 1. Oops, I'm sorry, it's 10, our first term. It's a sub 1 times R, my fault. It's a sub 1 times R. And then that R is to the power of n minus 1. I was mixing up my rules from before. It's the first term times the common ratio to the n minus 1. My apologies. So if we go back here, it's this right here. These are what we're using. Okay. So a sub n is the first term, which is 10 times R to the n minus 1. So here is the explicit rule from the recursive rule and the first term. So a sub n equals 10 times 2 to the n minus 1. Okay, so now you should be able to do problem numbers 41 and 44 in your exercises. Okay, example 6 is solving a real life problem. So it says here, a lake initially contains 5,200 fish. That's our initial number of fish in some lake. Each year, the population declines 30% due to fishing and other causes of death. So the lake is restocked with 400 fish every year. Write a recursive rule for the number a sub n of fish at the start of the nth year and find the number of fish at the start of the 5th year. Describe what happens to the population of fish over time. Okay, so here's a real world situation, and this would be really handy for conservationists to figure things out. So what you want to do is come up with a rule. So what do we want to do? Well, we have fish at the start of year n. That is our a sub n. And that's going to equal, well, if the population declines 30%, then that's 70% of what you had. If you lose 30%, you still have 70%. So 70% times fish at the start of the next year, year n minus 1. Okay, so if this was year 10, then this would be the next, that'd be 70% of the year before, is what they're saying. So there's 70% at the start of the year n minus 1, plus the new fish added. So this is a sub n minus 1, and then plus 400. We're adding 400 fish. So this is an arithmetic sequence where our common difference is 400. So we have a recursive rule where we have a sub 1. So our first year, we have a sub 1 is 5,200. Okay, just getting this right from our data here. So a sub 1 is 5,200. And let me not use a comma in this number, just put 5200. So I want to put a comma here. So a sub 1 is 5,200 and a sub n equals 0.7. So our rule is right here, 0.7 times a sub n minus 1 plus 400. Okay, or I could put a parentheses here too, or whatever, it doesn't matter. Okay, so there's our rule. A sub n is 0.7 times a sub n minus 1 plus 400. Part B says find the number of fish at the start of the fifth year. So I want to find a sub 5. So I want to write a sub 5 equals 0.7 times a sub 5 minus 1 plus 400. So finding the number of fish at the start of the 5th year, we have to enter 5,200 for our a sub 1 in a graphing calculator, and then take our answer and add 400. Okay, so what I'm going to do is here, open up my calculator. Okay, and hit clear. And I want to put 5,200 in my calculator. Okay, so there's my first term. So now I want to take 0.7 times my answer, right? 5,200, a sub n times the answer plus 400. So I want to take 70% of 5,200 and add 400. And when I do that, I get 4,040. Okay, so that's a sub 1. So let me recap this. It says find the number of fish at the start of the 5th year, enter 5,200, the value of a sub 1 in a graphing calculator, multiply it by 0.7 and add 400 to find a sub 2. So that's my a sub 2 right here. So let me just do this so I don't lose my calculator. So a sub 1 is 5,200. We just found a sub 2 by plugging it in our calculator, and we got a sub 2 is 4,040. So the population dropped. So I didn't finish filling this in. I'm just going to erase that. Okay, so a sub 5 we don't know yet, so I'm just going to erase that. So a sub n is our rule, and I plugged in a sub 1, multiplied it by 0.7, because a sub 2 would be a sub n minus 1, which is, and that minus 1 should be lower. It's not minus 1, it's a sub n all minus 1 down here. So a sub n minus 1 would be a sub 4 if I'm looking for the 5th term, and so on and so on. So you take the term before, multiply it by 0.7 and add 400. So that's what we're doing. So now I have 40. I'm going to say times. Actually, I don't have to do times. I just hit enter again, and it will do the rule over again. And now that's a sub 3. So a sub 3 equals 3,228. And I just have to hit enter now. Once the calculator knows the rule, it repeats it. So if I hit enter now, it is taking that rule from the year before, multiplying it by 0.7 and adding 400. So a sub 4 is now 2,659.6. I'm just going to truncate that because you can't have 6/10 of a fish. So I'm just going to drop that 0.6 off. And then I'm going to take and hit enter one more time. So a sub 5, 5th year, there are 2,261.72 fish. So that's going to be an approximation. You can't have 7/10 of a fish. So in the 5th year, we're going to have approximately 2,261 fish. So what is happening to this population? Describe what happens to the population of fish over time. Well, over time, the population of the fish keeps decreasing. But if I just keep hitting enter, what's it doing? Getting down to 1983, 1781, okay, and so on and so on and so on. 1442, 1409, 1386. I'm just continuing to hit enter here. 1346, 42, 39, 37, 36. So notice what's happening here is the decrease is slowing. It's going to decrease to where we're only losing about 400 fish. 30% of the previous would get you closer to 400. And then we add 400. And as you can see, it is getting down to, it looks like 1,333 fish. Okay, so 1,333, and it seems to be approaching that. So that's what we would say. Over time, the population of the fish in the lake will stabilize at about 1,333 fish. And so we state that. Okay, so that's what's happening with the population of fish if they add 400 every year. Okay, so now you should be able to do problem number 53 in your exercises. Okay, this is example 7, modeling with mathematics. So section 8.3, you used a formula involving a geometric series to calculate a monthly payment for a similar loan. And we need to remember that. So in this problem, we're going to borrow $150,000 at 6% APR, annual interest rate, compounded monthly for 30 years. The monthly payment is $899.33. It says to find the balance after the third payment. So due to rounding in the calculations, the last payment is often different from the original payment, and it says find the amount of the last payment. So you're given the conditions of a loan. You're asked to find the balance after the third payment and the amount of the last payment. So we need to make a plan. The balance after each payment depends on the balance after the previous payment. So we want to write a recursive rule that gives a balance after each payment, then use a spreadsheet to find a balance after each payment rounded to the nearest penny. Okay, so first of all, I have to come up with a rule. So it's going to be, we have a balance after payment is 1.005 times the balance before the payment minus your payment. Well, where did this 1.005 come from? The monthly interest rate is 6%, or annual interest rate 6%. So that's where this 0.005 comes in. So 6% is 0.06, but we are compounding monthly. So if we divide that by 12, we get 0.005. And I can show you that in the calculator. So it is 0.06 divided by 12. And it's 0.005. So 1.005 is your initial payment plus 5/100ths% monthly. Okay, so then what do we do? So we have a balance after the payment is 5/100ths% more balance before the payment minus the payment, because they're adding interest monthly. So that's an increase. And then we subtract our payment. So we come up with a plan. A sub n is the balance after the payment. Oops, clicked on the wrong thing here. A sub n minus 1. We have A sub n equals 1.005 times the balance before the payment, which is A sub n minus 1. And then finally minus our payment, our common difference of $899.33. So we want to use a spreadsheet for this. So I have one open. So I just went into Google Sheets. Here it is. And so for starters, I'm going to go into cell A1. If you haven't used these, hopefully you can follow along. And I made it bold, and I'm going to type in what we're doing. Well, we want to know what the payment number is. So you put that, and notice it's overlapped there. So when you go up and you go in between A and B and you see these double arrows, if you double click, it will widen it to what you need so it fits. Okay, and we want to know what our balance is after the payment, after each payment. So I want to know, I'm going to say balance after payment. And I'm going to make that bold. So if I click back in the cell and bold it, and then double click on the area in between, and there it is. Okay, so then I'm going to do payment 1, 2, and let's center these. So if I so what I did was I put a 1 here, I hit enter, I put a 2 here. So then when you click on this cell and drag, you're selecting those 2 cells. If you come over here, you want to center your data, and there it is. So once I do that, if I choose those 2 cells and then drag down, it will autofill. So I want to know, well, how many payments are there in 30 years? Well, 12 times 30 is 360. So I need to go down to 360. So I'm just going to grab these last 2 here. And I'm just going to go zooming down until I get to 360. See how it's going really fast if you're off the screen? And here we go. 360 would be right there. It went to 361 because my first row is our heading. So there are 360 payments. Now let's go all the way back to the top, and that's Control Home. And there we are. So we have the table set up. And so we want to use the spreadsheet to fill this in. And we have a rule. So if I click in B2 and I want to create a rule, we want to use, it's called round. So if I click on this thing right here, then there should be somewhere it says round. Let me see if I can find it. Let me pause this and I'll find it and then I'll show you where it is. Okay, so I just went to sum, I went to all, I come down here and I got into the R's, and then round is right here. And it says rounds a number according to standard rules. So it wants me to put a rule in here and it's going to round it. I'm not going to use that formula. I'm going to try something different, which is these up here. You can move your decimal place and that will do rounding as well. So let's try that. So what is my rule? Well, it's 1.005 times 1.005 times, and let me go back to my sheet here, our initial balance, $150,000. So it's 1.005 times $150,000 times 150,000 minus our payment, which was $899.33. And then it says, comma, 2. And it's all in parentheses. So let me just see what happens if I don't use round there. Oh, okay. So if I put the word round in the front, if I now go to my sum all round, now it's giving that rule. Okay, so you do have to use the round and you want to give it a rule and value and then the place. So you want the place value is the next payment number or the cell round place 2. All right, so I'm going to do that again. 1.005 times our $150,000 minus our payment, comma, and we want that place 2. Enter. Okay. And I don't want to autofill because it's not always going to be the same. So I'm going to reject the suggestion. And it rounded it. So it's 100. And then I can click on this and change it to dollars. And it's $149,000, 850. So after the first payment, what was our initial? $150,000. So think about this. You borrow $150,000. You pay $899.33, almost $900, and the payment only came down $149. So you paid almost, I'm going to do that after. Okay, so whew. All right, so if I said this, I'm just playing around now. If I take $150,000 and subtract what my new balance is, that is how much I paid it down. But I paid $899.33. So if I take this minus this, it shows how much interest I paid in that first month. I paid $750 in interest, and the principal only came down to $149. That's a front-loaded loan is what it's called. And so we're getting into some economics here and some financial algebra, if you will, but I like to show that as well. So now we're going to go to cell, the next cell, and we're now going to do the same command, which is round. And we have to type in 1.005 times. And then I don't want to do my $150,000. I don't have that balance anymore. I want this balance. So if you click on the cell above, it'll put B2 in there. And then you do minus our payment of $899.33, comma, and put a 2 and hit enter. Okay, now that I've done 2, all I have to do is drag this rule down. I always check. Did it drop? Yes. So now I'm going to drag this all the way down to 360. So this is much easier to do here than in a calculator. Okay. And then, so therefore there is not a 360th payment. You're not going to get paid back. You're not going to pay and then get paid 391 back. So I'm going to delete these 2. So the 359th payment, you're going to owe 890.97. And since your payment's 899.93, that's your last payment amount instead of the larger amount. And we found it. Okay. So what were we trying to do? Find the amount of the last payment. Notice we were paying 899.33 a month for those 30 years, but the last payment, you don't owe 899.33. You only owe 890.97. Okay, and so that's how you use a spreadsheet from your rule. Okay, so as I erase that negative 391, that's how much you would have overpaid if you paid the full amount. Okay, so now you should be able to do problem number 57 in your exercise. Okay, finally, we're at the end of this. This was a long exercise, but we're done. Chapter 8.5 exercises. These are the problems that I assigned. Thanks for watching and have a great day.